Hello everyone. In today's session, we are just going to learn about the queuing theory models, which is in the Unit 4. Okay, so where we are going to look about three models with finite capacity, infinite capacity with finite service channel. Okay, so before letting into the models whichever are covered in the syllabus are single server model with infinite capacity and single server model with finite system capacity, and finally multiple server model with infinite system capacity. So these three models are included in your syllabus. Before going to the deep into this model, let me go with an introduction of queuing models and how they has been coined. So actually, A.K. Erlang was the one who has been coining this queuing theory in 1909, and because many of us is experienced with waiting in a queue, which may be painful for waiting in it for a long time. Example like we may wait in a line in a traffic jam in cars and bikes and everything. And also like we'll be waiting in a supermarket to check out what we purchased, everything. So why there is a waiting in the process? So that is the main objective of the coining of the queuing theory. And because there has been a demand of service where the facility for service available, so why this so is nothing but there be a shortage in available of service, and there may be in a shortage of space, limit to the amount of service they can be offered. So, and based on this, the questions and the customers has been defined. So, how long might the customer wait, or how many people will form in the queue? So, all these questions has been with the answered by the queuing theory. Okay, so it is has been attempted to answer why we have to wait and why this waiting happens. Everything will be answered through this queuing theory. And actually what we define here, customer is not only the human being, it might be the one which is offered a service, the one thing with living or non-living offered service. For example, an aeroplane waiting in a line to take off, so there the customer is aeroplane. So similarly, there are a computer waiting to be run as a time shared basis. So computer is again a customer waiting to be run. Okay. So not only the customer defined here as a living thing like human beings. Okay. And there are many characteristic of queuing process. And for one is like arrival pattern. There are which design the queuing theory has designed with the aim of attempting the answer of why we have to wait and why it so happened, everything. So to answer it, we need some characteristic to design the process. So that is actually the arrival. First, we have basically six terms. One is arrival pattern of the customers, how they arrive, like finite, they'll be following a probabilistic model or deterministic model, everything decided. And second one is service pattern of the server, and third one is queuing discipline. And like we know when a discipline, like not only here when you're going with like I used to remember my schooling days when I've completed my task of the classwork, teacher asked to submit it on the table. So one who's finished first will submit on the table. But the people finishing the next, what happens is they'll be submitting above one who finished at the top. So it's the thing is whether the teacher will turn upside down and evaluate, make the correct checklist of the classwork, or else she'll be starting from the last who completed. So there'll be a discipline like one who comes first will be getting corrected at the last, or else one who comes first will be getting corrected first. So we'll have the discipline pattern of it. and the system capacity. So, like there'll be a restriction of spaces or so and so. So there'll be a capacity limit, and then the same thing, number of service channels it is designed. For example, we may have like servicing car servicing channels where they have multiple garage to service multiple number of cars at a time, or else if it is a very small showroom or some small service center, they may have only a single service servicing garage. Okay, and finally the number of servicing stages, where for example, when you're going for hospital, you have to go with the medical evaluation, everything. No, so in that first you'll go for one queue where the scanning will be done, and the scanning, before going for the scanning they will be asking you to pay for the scanning, so you will pay for it and you will go for the scanning, you will be waiting for the scanning in the queue, and then it will be offered with the scan, then you have to go. So stage by stage the service will be given, so that will be decided as number of service stages. And there are different types of arrival patterns we have, like bulk or batches, or like baked or reneged jockey. So there are multiple types. There are several types of arrival pattern of a customer request, and similarly, service pattern also there will be different cases. Like service may be a single or a batch. In general, one customer being serviced at a time by a given server. There are many situations where customer may be serviced simultaneously by a server. Example like a computer in the parallel processing, or people boarding a train, so on so. And where the service depends on the state of servicing, where a server may work faster if sees a queue is building up, or conversely he may be flushed or become less efficient. This situation in which a service depends on the number of customers waiting is depend on the service provider. So that is referred as a state dependent service. And as I said earlier, the queue discipline, we have peculiarly four different queue discipline. One is first come first service, or we'll say first in first out, last in first out, and random selection for service, and priority or primitive, non-primitive. So these are the four types of queue disciplines we categorized here. Not we, Erlong has categorized. And the system capacity, it might be a finite capacity where the waiting room will be only this much of numbers customers can be accommodated in the waiting room, and so on. So an infinite number of customers can also be the capacity. And number of service channels, like be a single service channel or multiple service channel we have. And the service stage, as I said, single service stage and multiple service stage. And single service stage example is nothing but we'll be going for a barber shop or like supermarket, theater, where will be service at a single stage. And multiple stages like account opening and going for canteen and medical reports histories, everything. So based on these six categories, Kendall has made a notation of the models. We'll call Kendall notations like A, B, X, Y, Z, where the first A refers the inter-arrival time, and B refers the service time, and X refers the number of parallel service, and Y refers the system capacity, and Z refers the queue discipline. So based on these five characteristics, the model has been designed. So, and yeah, Q discipline is that is a Q discipline, and the type of models where according to queuing is probabilistic model or stochastic model or deterministic model. Probabilistic model is nothing where there is uncertainty in both arrival rate and service rate, and are assumed to be a random variable. That will be the probabilistic model. And deterministic model is both arrival rate and service rates are constant. And there may be a model with mixed. whether the arrival rate or service rate exactly known and other is not known. And only we look on the probabilistic model, where usually here it is notated with mm1 infinity. The discipline is first in first out, and where we have mm1, m is nothing but this m refers here arrival rate and service rate and number of service channel, and this capacity of the system and q discipline. And this one finally is multiple service channel and infinite capacity and service discipline. So among all these three model, we are just following with only one discipline, first in, first out. Okay. So now let me go with the first model, where model 1 is a single server model with in system capacity, say infinite capacity, where so we'll just go with the model 1, where a single server with infinite system capacity, which is referred as MM1 and infinity. So we have the key for formulas to go for with this, where this P naught is nothing but where the system is idle. Here, this when the system is idle, we'll refer it as P naught. Okay, so which is nothing but 1 minus lambda mu, where lambda is here arrival rate, and mu here it is service rate. So where Pn is nothing but lambda by mu the whole power n, and this is specified. And coming to the second formula, the probability that the system is busy is identified as 1 minus P naught, where P naught is nothing but when the system is idle. So total probability is 1. From 1, this system idle is reduced, so it will be lambda by mu. So we'll say this as traffic intensity also. And third one, the expected number of customer in the system will be represented as LS, whereas lambda by mu minus lambda. And expected number of customers in the queue is LQ. So if it is customers, will be represented as L. And if it is in the system, it is suffixed with S. And if it is Q, it is with respect to Q. And coming to the next one, expected number of customers in non-empty queue. So that is nothing but in n, the number of customers exists. So it is mu upon mu minus lambda. And the expected waiting time of a customer in the system. So waiting time with the notation W in the system. So it is yes, 1 by mu minus lambda. And next one, waiting time of that a customer in the queue. So it is WQ. And next one is the probability that the customer in the system exceeds k, where the number of customers is greater than k, then it is nothing but lambda by mu the whole power k plus 1. And the probability that the number of customers in the system greater than or equal to k will be nothing but lambda by mu the whole power k. And the next one is the probability that the waiting time of a customer in the system exceeds t. So its probability of w greater than t is e power minus mu minus lambda t. And the probability that the waiting time of the customer in the queue exists. This is actually the system exceeds, and this is nothing but the queue exists. If its queue exists, it is like the service traffic intensity rho by mu times of e power minus mu minus lambda of t. And the probability density function of a waiting time. So PDF of the waiting time is calculated as mu minus lambda e power minus mu minus lambda of W. And the probability density function of waiting time in the queue, and this is like in the system. This is actually in the system waiting time. This is actually your PDF of your system, and this is your PDF of your queue. So it is lambda by mu of q. Whenever it is q, it is with the traffic intensity because the service has been rendering over there. So it is lambda by mu, mu minus lambda e per mu minus lambda of W when your W is greater than 0. That's when waiting time is greater than 0 and it is equal to 0, it is actually the busy time. Okay, so these are the basic formulas where it has been derived in the model, single server model with infinite capacity. So next let us look into a problem, an example to sketch those model. And before that, let me give a little formula where there is a relation between all of your LS, LQ, WS, WQ. We'll call that as a little formulas, the relation. So where LS is nothing but lambda times of WS, LQ is nothing but lambda times of WQ, and W is nothing but WQ plus 1 by mu. Because once you find one of the term, you can find the other one using this little formula instead of going with the direct formula. And Ls is Lq upon plus lambda by mu. So next let me go with the example. So here the problem. So customers arrives at one man barber shop. So one man barber shop is refers to the this single server. Single serve, okay. Barbershop according to the Poisson process with a mean inter-arrival time of 20 minutes. So lambda, here list lambda, so it's given minutes, so it is lambda is equal to 1 by 20 and customer spends an average of 15 minutes in the barbershop. That means getting serviced. So it is mu. And if an hour is used as a unit of time, in here it is given in minutes, so we have to use hours, so we have to convert it. And the question is, what is the probability that the customers need not wait for a haircut? So need not wait for a haircut means the system is free. So we'll go for idle. And what is the expected number of customers in the barber shop and the queue? Expected number of customers means so barber shop and in the queue. LS and LQ. System here it is barber shop. And how much time can a customer expect to spend in the barber shop? So barber shop is a system. So it is time. And finally the average time the customer spends in the queue, so it is WQ. And finally what is the probability there will be more than 6 customers, so it's greater than 6. So now let me solve it. And yeah, we have the few more questions. What is the probability there will be 6 or more customer waiting for a service? So the greater than or equal to 6. And what is the probability that the waiting time in the A system in a system and B a Q is greater than 12. So let me go for it. So it is given that here lambda is 20 minutes, so we'll convert into 60. So we'll take it as lambda is equal to 1 by 20. So accordingly it will be 1 by lambda is equal to 20. So we'll convert it into hours. So it is this case. So it is 1 by 3. So lambda is equal to 3 customers per hour. See, the arrival rate is 3 customers per hour. 3 customer is arriving, and mu is here a service rate where you are given with mu is equal to 1 by 15 minutes, and we have to convert this to hours. So it is 1 by 15 into 60. So you'll have 4. So 4 customers per hour. So first question is no need not to wait. Okay. So no customers in the system. So P naught is equal to 1 minus lambda by mu because the system is busy. So this system is busy, right? So lambda by mu is here traffic intensity. So from total traffic intensity is subtracted. So we'll find it 1 minus 3 by 4 is equal to 0.25. And second one is the number of customers in the barber shop. So L is lambda by mu minus lambda. We know lambda by mu, so it is 3 customers. And the next one is expected number of customers in the queue. So it is LQ. So lambda square mu minus lambda. Substitute lambda is equal to 3 and mu is equal to 4. So we will get finally 2.25 customers, approximately 2. And finally, next question is we will be finding the expected time of a customer spending in the barber shop. So it is waiting time in the system. So obviously it's 1 hour. And coming to the next, average time that the customer spends in the queue. So we'll be finding WQ, it's lambda by mu minus mu into mu minus lambda. So substitute it, we'll be spending 0.75 hours. And coming to the next question, the probability that there will be 6 or more customers waiting for service. And it is P of n greater than or equal to K. So it is lambda greater than or equal to K. So previously it was missed with the fifth question where it is like greater than 6, am I right? So fifth question, it is probability of n greater than k, which is lambda by mu whole power k plus 1. So here it is 6 is equal to k is equal to 6. So it is lambda by mu whole power 7. So lambda by mu is 3 by 4, the whole power 7. So that will be the answer for the fifth question. And if the customer is, there will be 6 or more customer waiting for the service, then it will be n greater than or equal to 6 is this case. And finally, the probability of waiting time in the system is greater than 12 minutes. So waiting time greater than 12 minutes is this case. W greater than 12 e power minus 4 minus 3 lambda 12 by. Accordingly, we will be calculating this.